Hey everyone, welcome to the lecture for 3.4 on partial fractions. I sometimes call this PFD for partial fraction decomposition, so heads up there. Okay, why do we care? Why do we want to do this? Well, one, it's super fun, but I know that's not the reason that we all have for doing calculus too. The reason that we do this from a mathematical standpoint is it's just really useful when we want to integrate rational polynomials, or when we end up doing a U-sub that brings us to a rational polynomial. And the cool thing, well, there are lots of cool things about polynomials actually, but one cool thing about polynomials is that there's always as many roots as there are degrees. So for any polynomial, let's say the degree equals n, then we know that there are n roots. And you might be saying, you're like, well, hold on a second. Wait, I know that the polynomial x squared plus 1 equals f of x. That guy has no roots. True, it doesn't have real roots. So when I say roots, I mean that they can be either complex or real. And the cool thing about complex roots is that they always come in pairs. And the real roots are always linear terms. And again, you might be wondering, you're like, hey lady, I don't care, why do I need to know this? It plays a role into partial fraction decomposition because, okay, complex roots, they always come in pairs. What does that mean? What does that mean? It's this, where it's this guy here. So here you're looking at a degree 2 polynomial with 2 roots, right? Because the number of roots always matches the degree, but both their roots are complex. In fact, you could break this up into, and this won't be on the test, so don't worry, but you could break this up into x minus I times x plus I, right? So it always comes into these complex roots. And and the complex roots are, moreover, they're in conjugate pairs. Stay with me, I'm getting to a point. When you multiply these conjugate pairs for these roots, it becomes an irreducible quadratic. It becomes something like x squared plus 1. So the cool thing about polynomials is, well, if you didn't think that was cool, I don't know, maybe like reevaluate yourself, but because that's awesome. But to break it down into the world of real numbers, polynomials always factor into, handwriting is not great today. They always factor into products of linear and irreducible quadratics. That's to say, like if I gave you the polynomial x to the 4th plus 1, for example, and I said factor it, and you were like, oh, Miss Bennett, no, that's already factored. I'd be like, I don't think so. Because I know that I can always take a polynomial to, the biggest thing that I can pull out of there is going to be a quadratic, right? Like that's the biggest chunk of leftover that you could possibly have. So it's got to be a combination of linears and quadratics. So don't ever tell anyone that a cubic or a quintic polynomial can't be factored, because you'd be dead wrong. Okay. Soapbox over. Let's just kind of refresh on polynomial long division or synthetic division really quickly. So in the case that we're trying to integrate a rational polynomial, the first thing we want to do is we want to make sure that the degree of the numerator is strictly smaller than the degree of the denominator. So the way that we do that I don't know if you guys, how much you remember synthetic division, but it's also another super fun thing from math that I just can't get enough of. So if I wanted to divide the numerator x squared plus 3x plus 5 by x minus 1, I would first set up my 1, 3, 5, which represent my coefficients of the numerator. And then I draw this little cool box thing. And then if I want to divide by x plus 1, I stick a -1 here, right? Because -1 is the root. If x plus 1 is a factor, -1 is a root. That's why the -1 goes in the box. I drop down. This guy always comes straight down. And then from here, synthetic division goes like this. You multiply, and then you add. So then 3 plus -1 is 2. And then you multiply, then I get -2, and then I'm going to add. So then I get, what's that, 3? Okay, cool. So now what happens is this 1, 2, 3. This really says that this is, so remember our numerator was a squared, a quadratic. So these numbers read off starting at the degree right below that, so linear. So 1x plus 2 as my constant, plus remainder 3. So it's not a great scientific way to write that. So really what I would write is, if I know my remainder is 3, I would write x plus 2, that's my whole part. And then the remainder 3, that just goes over the divisor. So my quotient is x plus 2, my remainder is 3, and my divisor is x plus 1 dx. And so from here, now we can see that this is actually a really straightforward integration where we're going to end up with a natural log and then just this reverse power rule business. So from here, I can just go 1/2 x squared plus 2x plus 3 ln x plus 1 plus c. So it's just a real quick little refresher on synthetic division. If you'd like to just see a quick long division, I personally didn't learn synthetic division until I had to teach it. Probably won't surprise anyone listening. I always just did long division. So long division is also super fun. Again, depending on your definition of fun. I do it the usual way. Okay. Shove that guy there. Divisor on the outside, and then I'm just like, okay, what times x will give me x squared? And then I just pretend like I'm in 3rd grade doing long division again. So then I subtract. So from here I would get 2x plus 5. So that will give me my plus 2. So 2x plus 2, subtract everything. And you can see that we end up at the same place. X plus 2 being our quotient, 3 being our remainder, x plus 1 being the divisor. So I don't care how you do it as long as it gets done. So now let's talk about the decomposition part of this. So I've hopefully drilled into the fact that we can always break up a polynomial into a product of linear and irreducible quadratics. We've refreshed on polynomial division, either synthetic or long division. And now we're going to learn something new. So when we break down a rational polynomial, if we have a bunch of non-repeated linear terms, then this breaks down to the sum of those factors, and that sum is going to have a constant on each one. So the first thing that you want to do is you want to break down the first thing you want to do is check that your denominator has a higher degree than your numerator. Check, done. The second thing you want to do is you want to totally factor your denominator as much as you possibly can. So since this is cubic, I know there's some factoring that can be done. So the first thing I do is I'll probably just be like, I'll pull out that x. And then hopefully it's clear how to factor the quadratic. So this is certainly not an irreducible quadratic. So I'm going to just do one more little step. So I get x, and then we're going to get x minus 2 and x plus 1. Okay, so now that we have everything with the correct degrees and everything broken down nicely, I see that I have 3 linear terms, and they're all distinct or non-repeated. So I don't have it like, well, we'll see those later. But anyway, they're all different. I'm sure you can tell. So the cool thing about this is the PSD, the partial fraction decomposition, says that 3x plus 2 over x by x minus 2 by x minus 1, this equals a. Even though in the text it kind of lists a1 through an, I don't suspect that we'll ever have more than like 5 constants. So I'll usually just use like the alphabet, A, B, C, D, etc. So I'm going to have a over x plus b over x minus 2 plus c over x minus 1. So it just says that you can break this into the sum of the linear terms with constants a, b, and c. And so the art of partial fraction decomposition is really just figuring out how to solve for a, b, and c. I'm going to show you 2 different ways. They're both in the text. In the coefficient comparison one, I do it a little bit differently than they do it. I think my way's faster. I'm pretty sure it is. Okay, so let's do the first one. The first one is just the idea, well, the whole thing really comes from the idea that you want to clear out this denominator. So if you take this whole thing, right, so if I rewrite this whole thing, which, bear with me. I'm only going to write this full out one time. So the idea is that you clear out the denominator on both sides by multiplying. Right, so if I do that, I mean, it's really obvious here on the left-hand side that these are going to cancel. But as you distribute the pink over the blue, like a over x by this pink thing, the x's will cancel, the a survives, x minus 2 survives, and x minus 1 survives. Similarly, when you distribute it over b over x minus 2, the x minus 2's cancel, and the x minus 1 and the b survive, et cetera, and so on. So it's usually easy kind of to pick up the pattern of how this is going to work. So what it all shakes down to is 3x plus 2 equals a times, and this is how I do it. I look at this and I'm like, okay, a is over x, so I'm going to write down everything except for x, which means x minus 2 and x minus 1. And then I save my brain power for other things, like, I don't know, embarrassing comments that I made 5 years ago that keep me up at night. I made a boo-boo. Okay. Oh my goodness gracious. X plus 1. All right, then b, the x minus 2 kills out the other x minus 2. So the only thing that survives is going to be the x and the x plus 1. And then for C, I just get the x and the x minus 2. So the first thing I'm going to show you is what I call the killer x method. So I choose x's that will make some of these terms 0. Because to me, the easiest thing in the world is to add 0 to something. So for example, if I said, if x equals 2, I chose 2 because it's going to annihilate the a, and it's going to annihilate the c, and then I'm going to be left with b times something equals something else. So 2 is a killer x. It may be the case, especially when we get to repeated linear terms, that you don't have enough killer x's to annihilate everything that you want to. That's fine. You could have like killer x's like less powerful sidekick that's like helpful x. You know, it's like any, like literally you could plug in any number and it'll help you find your values. Okay, so if x equals 2, then I would have 3 times 2 plus 2. So this is going to be a by 0 by 3. Again, I'm not going to write this full out every time. I'm just making sure I'm super clear on what we're doing. So then b times 2 times 3 plus c times 2 times 0. So this is a killer x, right? A is dead and c is dead. And I like this. So then I end up with 8 equals 6b. So that 4/3 equals b. And then I definitely want to make a note of that, right? Because I'm going to need that here. Okay. Cool. Thank you, b. You can go ahead and replace b with 4/3 in your equation, but I know that my killer x's are super powerful beings, and I don't need to for this particular example, but you could. Another killer x is going to be -1. So if x equals -1, then I get 3 by -1 plus 2 equals a times -3 times 0 plus b times -1 times 0 plus c times -1 times -3. So now I get -1 equals 3c, so -1/3 equals c. And that's another need to know value, right? Because I need you. I need c right there. My next and final and possibly the most convenient killer x to use is 0. So if x is 0, then I get 3 by 0 plus 2 equals a times -2 times 1 plus all this stuff, having so much fun. Okay, so 2 equals -2a, and so -1 equals a. Okay, so now I have a, b, and c. Just FYI, in the case that you don't have enough like killer x's, if x equals 0 isn't already a killer x, it's always a really good choice to be like helpful sidekick x, because it's such an easy value to plug in. Anyway, just a tip. Okay, what's the other method? Well, there's another method. It is awesome. The other method is to compare coefficients. So polynomials are just so amazing. Anyway, so another cool thing about polynomials is that they are uniquely defined by their coefficients. So a polynomial is really just a sum of powers of a variable centered at a point, which, by the way, we'll see later in the semester. And so the coefficients then dictate the polynomial. So, okay, why is that useful? I'll show you in a second. If we have 3x plus 2, then I have a by, so this is x squared minus x minus 2. I just want to make sure I got that right. Yes, I did. Okay. Then for b, I get x squared plus x. And for c, I get x squared minus 2x. So if I combine like terms, then what happens is, first of all, I'm going to write 0x squared here, which normally we wouldn't do. I think it's helpful in this instance. So for my x squared, my coefficients are a plus b plus c. And all those are my, that's for x squared, right? Because I get 1 from each. And then for my linear terms, I have negative a plus b minus 2c. And that was my linear term. And then for my constant term, I actually just have negative 2a. So the idea is that these are all supposed to match up. So this has to be this. And this has to be this. And I want more colors. And why I wrote 0. And this has to be this. So what you end up with is a system of linear equations. So I have 0 equals a plus b plus c. I have that 3 equals negative a plus b minus 2c, and then I get 2 equals negative 2a. And if you ask me, like literally anytime if I would like to solve the system of 3 equations and 3 unknowns by substitution or elimination, I would tell you absolutely 100% not. So if you like that, great, whoopee for you. I prefer to do it using matrices, which you all were supposed to learn in algebra, so hopefully you know it. But this is, you could convert this into an augmented matrix and then row reduce. And if you'd like to know how to do that on your calculator, I will make a video of that. So 1, 1, 1, 0, minus 1, 1, minus 2, 3, and negative 2, 0, 0, 2. So if you put this into row reduced echelon form, then what happens is you will get negative 1, 4/3, and negative 1/3. And what do you notice about those values? They are the same values that we get for A, B, and C. So not a coincidence. So this is A, B, C. I like it. I think it's fast. This is really the hard part about partial fraction. Like the majority of your time spent working these problems is going to be determining A, B, and C, or A, B, C, D, E, F, or whatever it is that you have to do for a problem. So now that we have that, we're finally ready to integrate. So let me do this. I'm just going to steal. Okay, so now that I have A, B, and C, I'm just going to rewrite this as my sum with A, B, and C. So I get negative 1 over x plus 4/3 over x minus 2 plus negative 1/3 over x plus 1. Yes, you can write minus 1/3 over x plus 1. Yes, you can write minus 1 over 3 times the quantity x plus 1. Yes, you can write minus 1 over 3x plus 3. However you want to do it, as long as it's done correctly, I'm okay with that. Okay, super. Negative ln x plus 4/3 ln x minus 2 minus 1/3 ln x plus 1 plus c. That's it. So the integration once you do PFD should be pretty straightforward, and that's your tell. So now we're going to try to put it together. We're going to divide, and then we'll do PFD. So in this instance, our degrees are equal. There's two ways to look at this. One, I'm not going to do synthetic division on this because I only know how to do that with linear terms with coefficient of 1. So you could do it by polynomial long division, which looks like this, x squared minus 4. And you want to shove that into x squared plus 3x plus 1. So I know I'm just going to get a 1 here, x squared minus 4, subtraction, magic, success, amazing. I hope I did that right. So, yeah, okay. So we get 1 plus 3x plus 5 over x squared minus 4 dx. So the 1, that's easy, that'll just be x. And then this guy is a quadratic, but it's not irreducible. It'll have 2 distinct linear terms. Another cool thing you could think about, this is kind of how I think about division, by the way. So I know this video is getting long, but I mean, it's already jumped the shark, so we're just going to roll with it. Let's say I had the number 17 over 8, and for some insane reason, I wanted to convert it to a mixed number. The way I think about it as a I'm like, okay, how many times can I write 8 until I can't stuff another 8 into there, and then what's left over? So this is how I think about division and remainders and stuff. So I have 1, 2, and then here's my remainder. So for me, I write this as 2 1/8. I'm going to do the same thing with our integrand. So if I have something over x squared minus 4, I want to be able to write it as x squared minus 4. I know I can't stick another x squared in there because I don't have room. I've already used up the 1x squared. So now I'm just going to add whatever I have to get back. So if I'm at -4, I know I have to add 5 to bring me to 1. And then I don't have any x's, so I know I got to bring a 3x into the fold. And so for me, I'm like, oh, cool. 1 plus 5 plus 3x over x squared minus 4. So that is another way to think, I don't know, about polynomial division, life, polynomials, fractions. Now that we've done that, we are ready to decompose our fractions using PFD, and thereafter we can integrate. So for us, we just have to take care of the 3x plus 5 over x squared minus 4. And I can already see that this factors very nicely. X plus 2, x minus 2. So now we're back to those distinct or non-repeated linear terms. So I know this is going to be a over x plus 2 plus b over x minus 2. So I get 3x plus 5 equals a times x minus 2, right? Because it's going to cancel. The x plus 2's are going to cancel, so it's just a and the x minus 2 that survives. And then I get b times x plus 2. And when I have non-repeating linear terms, I know I have enough killer x's to wreck shop, I guess. So if x equals 2, that's a killer x. I'll get 3 by negative 2 plus 5 equals a times 0 plus b times 4. So this is this and this. I'm off by a sign somewhere. Oh, right, because it's not negative 2. Okay, so 11/4. Good save. The other killer x is negative 2. So if x equals negative 2, then I get 3 by negative 2 plus 5 equals a times negative 4 plus b by 0. So this is negative 1 equals negative 4a. So 1/4 equals a. And so I can just go ahead and integrate. So I'm going to integrate 1 plus, right? Because here's my, let me zoom out a bit. Here's my original integral up here, right? I converted it to 1 plus this junk. And then the junk got converted to this cool thing where we have a over b. So a was 1/4. So I'm going to have 1/4 over x plus 2 plus 11/4 x minus 2 dx. So this is just x plus 1/4 ln x plus 2 plus 11/4 ln x minus 2 plus c. Again, you can totally do the comparison of coefficients if you'd like. So if you have 3x plus 5 over x plus 2. Oh, sorry, let me skip that step. We're here. I don't have any squared terms, so my linear is just going to be a plus b. And my constant is going to be negative 2a plus 2b. So from here I get 3 equals a plus b, and 5 equals negative 2a plus 2b. So if I throw that into an augmented matrix, I get 1, 1, 3, negative 2, 2, 5. And then that will row reduce into 1/4 and 11/4. So that's the other way to do it. Okay. So I'm going to do one more example and then I'm going to stop the video. So that way I'll give you a natural break. This one's going to be really similar, except we had to do a U sub first. So you definitely want to let U be sine. So that du is cosine x dx. And so this becomes the integral of 1 over u squared minus u du, which breaks up nicely into 1 over u times u minus 1 du. So now I just have 1 over u minus 1. And my linear roots are non-repeated, so this should be a over u plus b over u minus 1. I'm just going to do the killer x method this time and not the comparison of coefficients. Clearing out the denominator, I'm going to get a times u minus 1 plus b times u. So my killer u is 0 and 1. So if u equals 1, then I get, nothing happens to the left side ever. But if u equals 1, a goes bye-bye. And I just get that 1 equals b. And then if u equals 0, then it's still 1 on the left, but now I get a by -1 plus b by 0, so -1 then equals a. And so now I've got my partial fraction decomposition. So from here I can say that the integral of du over this guy equals the integral. So a was -1 over u. I always come back to this. I always come back here because if you, I'm saying this because I've done it. If you swap a and b, like if you said this was 1 over u minus 1 over u minus 1, like switching the a and b but keeping the denominators in the same place, you will get the wrong answer. So always come back to your initial breakdown so that you make sure that you're putting the right coefficients above the correct denominator. So yeah, a goes over u, and then b goes over u minus 1. So then plus 1 over u minus 1 du. So this equals -1 u plus ln u minus 1 plus c, and then we just back sub. So our u is sine, so we get -ln sine x plus ln sine x minus 1 plus c. And that's it. So I'm going to finish up the lecture for this section in a separate video, so stay tuned.